All right, folks, this is chapter 13, which is going to be chemical equilibrium. Now, these next three chapters, chapters 13, 14, and 15 in this book, um, they are all going to be interrelated. And in fact, the work actually gets easier. So, this is kind of an interesting thing. You may remember from last chapter I had mentioned something similar that as you get more information given to you, you're probably used to the chemistry problems getting harder as you get more information added. And these, what I call ice problems typically, or equilibrium problems, the more information you're given, the less work you have to do because you can start eliminating many things. All right? And so, what I want you to do for these chapters is you really need to focus on building up your fundamental understanding of chemical equilibriums. If you understand how an equilibrium works, what it is, and you understand the implications of that, then what happens is you can reduce the amount of math you have to do drastically. You can make these problems quite easy, actually. Most of these problems end up being a fraction of the work that you end up having to do as long as you understand what you're being told. Okay, so one of the major places that I see people that they'll just not do it, they will refuse to do it, they will not listen to me, and then they will just proceed to fail these next three chapters for a reason that really doesn't make a good sense. Is that they don't bother building up their fundamental understanding of, okay? So when I talk about things like this is what a K always is, an equilibrium constant always is, uh, they just skip that and they don't memorize it, they don't build it up, they don't practice it. They practice doing these long math problems over and over and over as if it's a form rote memorization thing that they should be able to do. It's not. Don't try to do these as rote memorizations. These are not one big formula you just plug in every time. Understand the principles. Work from the principles. Don't try to plug the entire thing in like you would some sort of math class. Here's the formula to do this one. Here's the formula to do this one. It's a terrible way to learn these things because oftentimes you'll end up failing. All right, now this is your tables of contents. Equilibriums. So a chemical equilibrium is going to be a state where the concentrations of all reactants and products remains constant with time. Now notice I'm talking about an overall state, which is usually called a bulk state. Okay? I'm not talking about the individual molecules. Individual molecules in chemical equilibriums exchange all the time. But in a chemical equilibrium, the overall concentrations will remain the same. So this is obtained by reactions that take place in a closed environment. If you have an open environment, then your different molecules can escape. Think about when you're breathing out. You breathe out the CO2, and then it gets replaced by the oxygen because you're in an open environment. And so you can't get that CO2 back to be in an equilibrium, right? Another way of thinking about this is if you were taking a soda and watching it, it's an equilibrium. And then if you start pouring it out, well, it's no longer an equilibrium, is it? Because it's going to be having portions of that removed. All right, now, this may favor either products or reactants. If the products are favored, the equilibrium position of the reaction will lie far to the right. If the reactants are favored, then it will lie far to the left. Another way of saying this is your concentration of products may be higher, or your concentration of reactants may be higher. I didn't mention that products or reactants have to be equal here. Notice that. Okay. This is actually one of the major sticking points with students is somehow some students just get it in their heads that equilibrium means that the amount of products and the amount of reactants are equal. That is not true, okay? I repeat, the amount of products and amount of reactants do not have to be equal in an equilibrium. What is true is that you have no overall change of the amount, the concentrations of products and reactants in an equilibrium. That's what's equal. Not reactants equal products. That's not true, okay? All right, now, visible changes cannot be detected in reactions that have achieved chemical equilibrium. So, on a molecular level, you have this frantic activity. You have conversion of molecules back and forth in this reaction from reactants to products, products to reactants. They're continuously changing, okay? And so the equilibrium is not static. It is a highly dynamic situation. However, overall, your concentration of reactants and your concentrations of products, those will stay the same. So this right here shows you, if you remember right here on the left side, this is very similar to the reaction rates where I talked about before. So here we have reactants, they're being converted to products, so they're going down. Right here we started with no products, and so they are going up. Eventually what you're going to see is if you go further right, you give this more time, you will make enough products and lose enough reactants where the reaction rates, how fast reactants go to products and products go to reactants, will be equal. And that will give you an equilibrium where your concentrations of reactants and your concentration of products do not change. And this equilibrium, as long as you keep this in a closed environment and you don't lose anything, it's going to just stay like that for essentially ever, okay? For longer than you would ever want to deal with it. As long as nothing gets lost, it should theoretically just stay like that forever. All right, now, right here we have a molecular representation of reaction that we just saw in that graph, okay? And so you see at the beginning you have all your reactants. Slowly they will convert to products, and we're seeing products start to pop up here. See that? This is CO and H2O. Here we have the hydrogen gas and CO2. And we start seeing products pop up. Now eventually we get to a state where we're going to have our number of reactants and products where they are their equilibrium amounts. And what this will cause is, yes, they will convert individually. So the individual molecules, they are still doing the reaction forward and backwards, okay? But the equilibrium state has the overall numbers of molecules or the overall concentration staying the same. Okay, so these are the reaction rates. In this case, we have our forward reaction, which would have been the reactants going to products. And at the beginning, because there's only reactants, this will go very fast. And then eventually this will tail off. It will get slower and slower and slower because you have less and less concentration of reactants to take part in this reaction. The reverse rate will start increasing. In the beginning, it's zero because you don't have any products to do the reverse reaction with. But as you gain more and more concentration of products to this reverse reaction, it will increase. So your equilibrium always happens where the forward and reverse rates are equal. And that is what is equal in an equilibrium. Okay? It is the forward rate and the reverse rate of that equilibrium reaction. So, some of the factors that will determine the equilibrium position of a reaction. The position is specifically the concentrations that would establish that equilibrium. So, it would be listing out the concentrations of your reactants and products. That is what we refer to as the position. Okay? What is going to determine this? Well, initial concentrations, relative energies of reactants and products, the relative degree of organization of reactants and products are the three major factors. And I'll go into more detail on each of these, and we're going to use some different visual representations that you can use in your head to help you envision these. but this is your overall introducing you to these. So, what are the characteristics of a chemical equilibrium? The concentration of the reactants and products in a given chemical equation will remain unchanged because the system is at chemical equilibrium, the forward and reverse reactions are very slow, the system moves to equilibrium at a rate that cannot be detected, or applicable. This is applicable, by the way, to nitrogen, hydrogen, and ammonia mixtures at 25 degrees Celsius right here. It just moves so slowly you would not be able to sit there. Remember that when we're talking about equilibriums, not all equilibriums are going to be fast. Some of them will be so slow that you will not be able to detect them in a given time period. For example, right now, there is an equilibrium that's happening in your water and your pipes. And this equilibrium states that it will build up limestone, essentially, in your pipes over enough time, and they will turn to stone. Obviously, this is happening very slowly. So thank goodness it's happening very slowly, right? Or else you'd be in trouble next time you try to take a shower. All right, now, right here we see another example of equilibrium. Again, this is that equilibrium we talked about just now, where we'd have ammonia, nitrogen, and hydrogen. So your reactants are getting used up to make ammonia. And what we're seeing is this right here is actually very, very slow, okay? If you tried to do this in lab at 25 degrees Celsius, you would essentially never see equilibrium being reached. However, if you give it enough time, it will establish a chemical equilibrium. All right. So let's consider the following equation. CO plus H2O yields CO2 plus H2. Notice this right here is the symbol again for equilibrium, which you've actually seen at least half a dozen times, if not more than a dozen, depending on what your General Chemistry 1 instructor showed you, which they should have. You should have seen this in General Chemistry 1. All right. So which of the following must be true at equilibrium? A, CO2 equals H2 because they are a 1-in-1 mole ratio in your balanced equation. Remember, that was a product here, and H2 is another product. B, the total concentration of the reactants is equal to the total concentration of products. C, the total concentration of products is greater than the total concentration of reactants, is greater than products. The total concentration of products is greater than reactants. Or none of these is true. Well, in this case, this is none of these are true. So let's look at this again. What are true at equilibrium? Well, we didn't say any other details about this equilibrium. And so what you may have noticed is we didn't tell you, did you start only with reactants or did you start with products? You could have had 1 mole of each of these at the beginning, and then an equilibrium was established. Or you could start with 1 mole of each of these, and then they make this and establish an equilibrium. We didn't say, we didn't not indicate in any way whatsoever. So this doesn't have to be true, because we didn't say anything about that. We just said it made an equilibrium. The total concentration of reactants is equal. None of these have to be true for equilibriums. Depending on the conditions that it's under, some of these could be true. But none of these have to be. None of them are factors that would actually make it an equilibrium. Okay? So none of these actually has to be true in this case. Which of the following is true about chemical equilibrium? It is microscopically and macroscopically static. By the way, typically you would just say micro or macro, and you wouldn't bother saying the entire word microscopically or macroscopically. Anyways, both are static. That's not true, is it? We talked about the fact that microscopically on the molecular level, these things are highly dynamic. Microscopically macro, they are dynamic. Well, no, actually, the definition of chemical equilibrium tells you the macro level has to be static, doesn't it? It has to stay the same. It is microscopically static and macroscopically dynamic. Well, we actually flipped these, didn't we? It is microscopically dynamic and macroscopically static. That one's true. Because, yes, the individual molecules, they are exchanging all the time, but macroscopically, the concentrations do not change. And that is actually the definition of a chemical equilibrium. So, the law of mass action. Ironically, almost everybody I teach this to quickly forgets the name of this. That's the law of mass reaction. You'll be really impressing me if you remember that this is law of mass reaction. This is incredibly easy, actually. This is something that, if you thought about this a little bit at all, it actually would have popped out in your head. So, law of mass action, this is actually based on the fact that using 1 mole of this creates 1 mole of that if you were to go all the way over here, right? If you had 100% converted reactants to products. And so, this statement I'm going to teach you, which is actually incredibly easy to remember, it almost rhymes, is something that is actually based on a basic tenet you learned in General Chemistry 1 the first day, and you really probably should have learned during middle school, hopefully. If you did not learn during middle school, then somebody really needs to talk to your Board of Education from wherever you took middle school. Because they have completely failed. It's actually an elementary middle school objective to learn these, but oh well. All right, so here we have different chemical species in an equilibrium. How do I know this? Well, these are different species right here. A, B are reactants, C, D are products. This means equilibrium. And so these would then be their coefficients. In this case, we're using just letters so we can designate these, right? The exact letters don't matter. J, K, L, M, whatever. So, the law of mass action is going to represent what is called the equilibrium expression. From the fact that the law of mass action, that you, remember this is a law, so this is not theory, this is repeatedly observed. From the law of mass action, you can get the equilibrium expression. And this equilibrium expression is very, very easy to determine from your balanced reaction here. And it is the equilibrium constant. Notice that is a capital K for equilibrium constant. All capital Ks that you're going to see in chemistry, biochemistry, all of these subject matters are going to be, and you may have seen from biology, are going to actually be different types of equilibrium constants. There'll be slightly different ones, which will have different symbols down here. But they are all this equilibrium expression. That's what a capital K is. It is an equilibrium constant derived from an equilibrium expression. Now, this equilibrium expression, this is always, and I want you to repeat this with me. I'm going to say it several times. I want you to get to the point where it feels like a chant, because it will drill it in your head. And this is the part that I truly do not understand why students do not memorize this, get this pat down. We have 3 chapters that are all going to depend on you being able to do these equilibrium expressions. And students that do this, you automatically are going to be able to get at least 20% of the questions that I ask you, period, just by knowing this. Very easy to do. If you don't get this down, automatically you're going to miss 20% of the questions, and really you're missing about 50% of the questions that you just won't be able to do at all. So, equilibrium expression is always products over reactants. Try with me now. K is always products over reactants. Try one more time. Products over reactants. Notice it almost feels like a little chant you can do, doesn't it? And so you always take the concentration of your products to the power of their coefficients over the concentration of your reactants to the power of their coefficients. Notice that's JK, JK. And so this is incredibly easy to write out whenever you see a balanced reaction like so, which will be a basic skill that you're expected to do for almost every single problem in these next 3 chapters. And do it repeatedly. It's something you should be able to do as if you're breathing. You literally look at this and you write this down. You don't have to do any work. Okay? That should be easy. Please practice. Now, square brackets, these indicate when you have a chemical species inside of a square brackets in an equation that these are the concentrations in molarity of the chemical species at equilibrium. So these square brackets here are always the concentrations of these species. This is a K, which is a equilibrium expression. This is what this is. And this is an equilibrium constant. Notice the word equilibrium in all of these. And so these values always have to come from the equilibrium conditions. They cannot come from anywhere else. They have to be from the equilibrium conditions, because this is again, equilibrium expression. Notice the equilibrium. Let me say it one more time just so you can be sure. Equilibrium. All right, so K is an equilibrium constant. That means everything that's put in for it, everything you do with it, is for equilibriums, not any other state. They are only for equilibriums. So let's try this out and do a little bit of math. So let's write the equilibrium expression for this following reaction. Hopefully when you just see this, you can automatically just pop up. So it has to be K, well, it's always products of reactants, right? So it has to be the concentration of this to this power times the concentration of this to this power over, divided by, the concentration of this to this power times the concentration of this to that power. So we give our law of mass action, again, it is the products right there, divided by the to the power of their coefficients, divided by the reactants to the power of their coefficients. And so again, that is always how it is. You just write literally the chemical formula right here and then put brackets around it. That stands for the concentration of this. That stands again for the concentration of this. And there you go. All right, so if we observe the following equilibrium concentrations for the synthesis of ammonia at 127 degrees Celsius, which is the Haber process, by the way. This is the major way that you produce most the ammonia that would go in things like fertilizer, if you're curious. And so right here, we have our equilibrium concentrations. Well, that tells us that we could plug these in and calculate a value for K, because these are the concentrations at equilibrium. So if we want to calculate the value of K at 127 degrees Celsius for this reaction, then we're going to use these values. So let's calculate the value of the equilibrium constant at 127 for this following reaction, and then we'll calculate the value of the equilibrium constant at 127 for this reaction. Now notice in this interactive example, we're actually going to lead you into understanding a principle on how to manipulate different Ks for different reactions. So note, first off, that when we write our equilibrium expression, which is how we write the expression for K, the equilibrium constant, it's the coefficients that go into it, right? And so if we do things to the coefficients, that's going to change our equilibrium expression. Another thing that you can think about is we put products of reactants, right? So what happens if we flip the products and the reactants? So here NH3 is reactant, N2 is a product. And so this would be products on top, reactants on bottom here. This one, on the other hand, has been flipped, hasn't it? And so here we have what used to be our reactant as our product. And our products that before and B as our reactants. And so if you think about this, our equilibrium expression is going to be flipped, isn't it? What used to be on top will be on bottom for C. So first let's do A. We've already figured the equilibrium expression out for A. So right here we have our Haber process. We go ahead and put our equilibrium expression. Again, it is product, right there, to the power of its coefficient, divided by the reactant, and then its coefficient is 1, so we don't put anything. Or we just put 1, either way. And then right there is your reactant, and again we put its coefficient as the power. Then we plug in our concentrations we were given at the beginning of this problem. And so we plug these in. We do the math. Again, I would always recommend you go ahead and just do the math separately. So you take this scientific notation right here, you put it in parentheses, put it to the power of 2, figure out that value, write it, and then do the math piecemeal. Now, this will give us a value that's 3.8 times 10 to the 4th. You will notice that that's actually quite a large value. You will also notice that the equilibrium expressions are always written without units. And so you, for once, do not have to write units. My goodness, we finally freed ourselves from units, haven't we? All right, now, right there's our K value for A. Excellent, we've done A. So the next thing is determine the equilibrium expression for dissociation of the ammonia. All right, so in this case up here, you will notice that this is making ammonia, isn't it? See, we've taken the elemental components of this, nitrogen, hydrogen, and we've made ammonia from that. And so that would be your formation. Your decomposition would be the reverse. So we're going to have to flip this to get the decomposition. And so when we flip that, what's going to happen? Well, your product is going to be flipped. Your product and reactants will flip, right? And so you will reverse this equilibrium expression. It will go upside down. Okay, so K prime. Prime means a modified condition. This is for the dissociation of ammonia. Now we're going to reverse these. Remember, your product is now your reactant. Reactant is now product. So that directly means you will do the inverse of the previous equilibrium expression. So again, in this case, the ammonia is going to be on bottom because that is going to be, well, products of reactants, so that's a reactant. This right here is your components, the elemental components. For dissociation, you're breaking into the elemental components, and these are going to be on top. Again, they have the same coefficients, so you're going to have these same powers. Now, I know that you could write this out. It wouldn't be that difficult for you to reason that out. But let me tell you, there is a shortcut. You can take the previous value of K that we got before, and you can recognize that if you reverse the order of reaction, if you are, instead of forming it, you're dissociating it, then that means your value of K is going to be the inverse. Because if you flip your products and reactants, you have to do the inverse or flip your equilibrium expression. And so you can very easily just take the value of K we got before, take 1 divided by that value, and that will give you your new dissociation equilibrium constant, which is 2.6 times 10 to the negative 5. Okay, so C, let's determine the equilibrium constant using the law of mass action for that new reaction. So I should have copied that new reaction right here. You will notice that in this case, again, this is going to be similar to the previous one. We have the formation of ammonium right there. So it's like this one right here. But instead of doing these as whole numbers, and these are now fractions. And so when we generate this, again, we're going to do products of reactants for the equilibrium expression. This right here is your product. It's going to be to the power of, well, 1. This right here is your reactant, so it's on bottom, the denominator. And this is going to be to the power of 3/2. Yes, you can do that. You can do 3/2. By the way, if you're curious, the next one is going to be this concentration to the power of 1/2. If you do not know this already, to the power of 1/2 is the same as saying square root. Okay? This right here would be like taking the square root and then taking that to the power of 3. Okay? And that's actually what, when you take power of fractions, that's what those do. Those are, the fractions are actually like doing cube root, square root, etc. Cube root would be to the power of 1/3. So, we take this, and right there is our answer to problem C, which would be, again, there's product over reactant. We take this to the half, 3/2. All right, if we compare that to A, you will notice what we've done is when we halved all of our coefficients, we also took K to the power of 1/2. That's actually what that does. So if we were to compare these to generate problem C's equilibrium expression and equilibrium constant, all we have to do is just take A's, the equilibrium constant we got from A, and put it to the power of 1/2, which again is what we did to all of our coefficients. We halved all of our coefficients. So we can just take that value for K we got in the beginning in part A of the problem. We take it to the half power, and that will give us our value for part C right here, 1.9 times 10 to the second. So let's consider this following reaction right here. We have our equilibrium expression here. So if we reverse this original reaction, what's going to happen? Well, we just flip all these terms, right? And so thus we get this one right here. So if we reverse an equilibrium, the equilibrium constant has to be the inverse. All right, so what happens if we multiply our coefficients and our equilibrium? Well, then we're going to multiply the powers by that same number in our equilibrium expression. Or another way of saying that is we take that multiplying factor. This could be 1/2, this could be 2. We have to do that for all this. Remember, this is an equation. And so we would take that. So if this is 1/2, this would be K to 1/2. If this was 2, this would be K to 2, etc. All right, so this right here shows you the synthesis of ammonia at different concentrations of nitrogen and hydrogen. So right here you can see we start with nitrogen and hydrogen. And when we reach equilibrium right here, you'll see that it will make some ammonia. And this will again have this value of K equals 6.02 times 10 to the negative second, which is again its equilibrium constant. Okay, so what if instead of starting with these reactants here, nitrogen and hydrogen, we instead start with NH3? Well, what we end up doing is we make a different equilibrium concentration setup, but we're going to have the exact same K. What if we start with a different set of concentrations? Well, again, we'll get a different set of equilibrium concentrations, but if we were to plug those into our equilibrium expression, we would still get the same K. So, for a given set of reaction temperature and a reaction, you're going to have the same value of K. It does not matter what the initial concentrations are. You will still get the same equilibrium constant. So you could plug in any set of initial concentrations. They will still give you this same equilibrium constant here. And that means that you will get a set of equilibrium concentrations that will always be derived from this equilibrium expression. Okay? So the equilibrium position, this is going to refer to each set of equilibrium concentrations. There can be an infinite number of positions for a given reaction and temperature. This depends on the initial concentrations. Your equilibrium constant, on the other hand, there's only one constant for a particular system at a particular temperature. This will remain unchanged. It will not change depending on initial concentrations. For that reaction at that temperature, one equilibrium constant for any conditions otherwise. So this is going to depend on your ratio of concentrations. This is how you can derive it. And you can also get, if you have an equilibrium constant, you can get the equilibrium concentrations for any given system. So you can figure out the position from it. The following results were collected for 2 experiments involving the reaction at 600 degrees Celsius between gaseous SO2 and O2 to form gaseous sulfur trioxide. So experiment 1, here we have initial conditions. Here we have a set of equilibrium conditions. And here is experiment 2, where we have a different set of initial conditions and another set of equilibrium conditions. So let's show ourselves and prove that the equilibrium constant is the same in both cases. And so first we need to get the balanced equation for this. This right here is your balanced equation. 2SO2 plus O2 yields 2SO3. From our law of mass action, we get our equilibrium expression, which is so, products over reactants. And you can see right there again, of course, we have our equilibrium coefficients showing up right here as our powers. Alright, so the next thing we're going to do is we're going to plug in our concentrations into that equilibrium expression. That will allow us to figure out our equilibrium constant. So for experiment 1, we plug the values in for the equilibrium concentrations, and we get a value for K that is 4.36. For experiment 2, we go ahead and do the same thing. We plug these values in, and because this is experimental data, it's the real world, not fake, we get a value of 4.32. Have you ever heard you're not doing real work if everything's perfect? Hopefully you have. If you have not, it's the truth of the universe. Okay? You're not doing real work. One of the ways you can tell if somebody did not do the experiments, and this is how I actually figure out if people were cheating on the labs. If the data is perfect, it's not true. You're always going to have some degree of error, okay? And this last error point right here, this would be the sort of thing you'd get from rounding errors. This right here is a normal sort of experimental error we would expect. And so these values they're the same. They just have a little bit of experimental error, maybe a few errors in measurement, whatever. So yes, we have proven that that's true. Doesn't matter what our initial position was, we get the same equilibrium constant for both of those experiments. So which of the following statements is false regarding chemical equilibrium? A system that is disturbed from an equilibrium condition responds in a manner to restore equilibrium. B, the value of equilibrium constant for a given reaction mixture at constant temperature is the same regardless of the direction from which equilibrium is attained. C, when 2 opposing processes are proceeding at identical rates, the system is at equilibrium. And D, a system moves spontaneously towards a state of equilibrium. Or is it E, all of these statements are true? Well, hopefully you had trouble when you went through these going, man, none of these are wrong. These all seem right. Because they all are correct. That these all describe different factors that are true for equilibrium. And so yes, they are all true. Equilibrium constant for this reaction here is 2.1 times 10 to the negative 6. So determine the equilibrium constant for this reaction. So what we do is we look at these two. How are these different? Well, A is still in the same place, B is still the same place, C is still the same place. So they're going in the same direction. This, however, has a 2 in front of it. So we've multiplied this entire thing by 2, haven't we? And so what does that mean we have to do to the equilibrium constant? Well, we're going to have to take this to the second power, aren't we? And so we take that to the second power. So that is 2.1 to the second power times 10 to the negative 6 to the second power. If you don't know, in these cases, you can very easily estimate this. 2 to the second power is 4, so this has to be 4 point something. Right here, this 10 to the negative 6, when you take something with a power like this to the second power, these multiply. So negative 6 would multiply by 2, and that would give you negative 12. All right, so consider the ideal gas equation. Right here we have PV equals nRT. Hopefully that rings some bells. You should have learned that last semester and gotten very used to that last semester. This right here is just a rearrangement of that same ideal gas equation, or ideal gas law equation, which may be how people said it. It depends on what book you look, what it's called exactly. Now, this right here, we've just rearranged it so that we've gotten moles and volume, which is in liters, all into one term. Notice what moles over liters is molarity, or concentration, isn't it? And so what you can see here is the pressure equals the concentration times R times T in Kelvin. So C, it'll be the molar concentration of a gas. So C, which is moles over volume, is going to be, again, the moles in of a gas per unit volume V. Now notice this moles in this gas. This, we're really in this case talking about a single species in this case, so keep that in mind. Alright, so right here what we see is we have our K. We've been working in concentration units before, right? And we haven't really mentioned what sort of concentrations we're talking about. So typically we're talking about C, concentration, or another way of saying that is molarity, right? That we typically have been using for these solutions. And so yes, you can calculate this in molarities, concentrations, and that would be a K sub C, which would be an equilibrium constant calculated in concentration. Now, you can also calculate these in terms of partial pressures of the gas. Remember, the partial pressure is just an easier way to determine the concentration, if you will, of a gas when it is, of course, all vapor phases. So right here we see that a K sub P is going to be the equilibrium constant with respect to pressure. And so, of course, we have the same thing. It's still products of reactants. It's still to the powers of their coefficients, just like before. It's just you're going to be using pressure terms, partial pressure. And so, again, this will be unitless here. These will be in partial pressures in atmospheres. So, in these equations, K and Kc are going to commonly be used symbols for an equilibrium constant. That's in terms of concentrations. You will notice that Kc is the correct term. However, the concentrations are much more preferred to do these with. Most people will just use K and won't even put the C. They'll just put K. Because the concentration one is just by far and away the preferred one for most scientists. Kp is the equilibrium constant in terms of partial pressures, though. So let's consider the reaction for the formation of nitrosyl chloride at 25 degrees Celsius, which is this reaction right here. In this case, these are all gases. It is much, much easier to figure out partial pressures here. Figuring out the concentrations of these in molarity would take you a lot more time. You couldn't just measure those. And so we figure out here that the partial pressure of NaCl right there is 1.2 atmospheres. Here we have this one, and here we have this one. So let's calculate the Kp for this reaction. So again, we figure out our equilibrium expression, products over reactants, and again, they're to the power of their coefficients, just like before, just like every other time. I'm going to stop saying that. Hopefully at this point you mostly got this. If you don't, pause the video and learn it, okay? You're just not going to be able to have any real chance of learning anything else if you don't get this down. Let me just say that right now. For the next 3 chapters, if you don't have that down, products of reactants, that's your equilibrium expression. Literally nothing else for the next 3 chapters will make any real sense. Okay, so we just plug in our numbers that we were given in the previous slide. There, there, there. We take them to those powers, and ta-da, we have our Kp when we do the math. Make sure you do these in sections. It is very, very, very easy to screw up the putting these into a calculator and getting the wrong number. So consider the following general reaction here. The relationship between a K and a Kp, another way of saying this is a Kc and a Kp, is this relationship right here. So Kp equals the Kc times R, gas law constant, times T in Kelvin, temperature, to the change in moles. Now, what does this change in moles mean? Well, this is the sum of the coefficients of the gaseous products minus the sum of the coefficients of the gaseous reactants. So let's look at that a different way. So when we talked about the ideal gas law, remember that the number of moles of that gas, it didn't matter what what molecules those were. All we looked at was how many total moles there were, right? So what happens if you break up and you had 2 moles of gas, you now have 3 moles of gas on the other side because you broke part of these in half or something? Well, you'll get more moles of gas, right? And so that would give you greater pressures. And so yes, you do have to take into account that change in moles. Don't forget that. That's one of the sticking points that people have trouble with on these conversions. Okay, so for our general reaction, if we were to do the math, we see that the Kp would have these coefficients right here. If we were to do each of these conversions, we would see that to go from the pressure, we would have to take that pressure was equal to the concentration times RT. And so what we see is when we're looking at the concentrations times RTs, these would get distributed through their powers. And so what we see is the coefficient actually ends up being distributed through to each of these RTs, don't they? If we go ahead and take all of these C's to their powers and collect them up into one section, then that again is going to be our equilibrium expression in terms of concentration, right? Like this is for pressure. But what we see is those RTs, they don't cancel, do they? What they do is they would get collected up like so. We can then transform them. If you take 1 over 10, that's the same thing as 10 to the negative 1. Okay? And so when we have powers in the denominator, they can be represented by negative powers in the numerator. And so we have just flipped this up here, taken these as negatives, we subtract those off of these, and we get that change in N. And so what change in N is, it's the difference in the sums of the coefficients of the gaseous products and reactants. And they come from the fact that this conversion, this unit conversion going from pressure to concentration, this is going to have RTs that have the powers that are those coefficients. That's where those are coming from. We're just collecting them all up into one term, so it's much, much easier to deal with. Okay? So the text gives an example for which K equals Kp. The text states that this is true because the sum of the coefficients on either side of your balanced equation is identical. What if you're told for the reaction K equals Kp and the sum of coefficients on either side of the balanced equation is not equal? How could that possibly be? Okay, so try to give this a little thought first. Yep, I'm waiting for you to think. I know, it's included in the video. Okay, so really you should pause if you want to think. Anyways, I'm gonna stop. Now, this could be true, yes. The way this could be true is, well, is a solid a gas? Is a liquid a gas? No, neither of those things are gases. And so the thing that has not been introduced to you yet and that you have not figured out yet is things like solids and liquids. These don't get included. They don't have concentrations or partial pressures. They are what's called unity. They are represented as, they are not represented in an equilibrium expression. And so you could have it where the coefficients on either side are not balanced, where you don't have 1, 1, 1, 1, but you could have something like 1, 1, whatever number, solid, and then 2. And so you'd have an equal number of moles of gas on each side. And that would be true. That would mean K is equal to Kp, as long as you have an equal number of moles of gases on both sides. So let's go ahead and try this out a little bit. Use the value of Kp obtained in example 13.4. Let's calculate the value of K at 25 degrees Celsius for this same reaction. Alright, so the first thing we need to do is we need to figure out the difference in moles on both sides. Here we have a 2, 1, that would be a 3. Here's a 2. So again, we're going to do products over reactants, so products minus reactants. And that is going to give us 2 minus 3, which is a negative 1. So again, products minus reactants. How do I know this has to be products minus reactants, by the way? Again, whenever we're looking at powers, the stuff in the numerator is positive, the stuff in the denominator is negative. And hopefully you remember that back from your math classes. If not, please do a little reviewing. Okay, now, this right here is our formula. We're going to plug everything in. This is the gas law constant that determines what units we have to use. And if you remember your gas law constant, or looking at the sheet I give you guys for every exam, then this is going to be in kelvins. We were given it in degrees Celsius, so we have to add 273 to get kelvins. So we plug all of these in, and that gives us this relationship right here. And we plug the numbers in there. So we have Kp from the previous problem. This right here is R, the gas law constant. That's the temperature. It was a negative 1 right here. That caused this RT to be on the bottom below the K. And so we would multiply that to the Kp, which is what we have here. And that will give us, well, our K, our Kc, is 4.6 times 10 to the 4th power then. Notice we never need any units for values of K. So for which of the following reactions does K equal Kp at the same temperature? Alright, so what are we looking for again here? We are looking for equal number of moles of gas on both sides. So here we have 4 moles, 1 plus 3, 4 versus 2. No, that's not true, is it? Right here we have a solid. We don't even have a gas on that side, so that can't be true. Right here we have 1, 2, that's 2, 1, 2, that's 2 again. That's an equal number of moles, isn't it? Cool, we found our answer. And then the last one is a solid. This is a gas, this would be 1. This is a gas, this would be 4. That's not equal. And so yes, it is answer C. That is correct. That's an equal number of moles on both sides. That would make your K equal to Kp at the same temperature. Why would that be? Well, mathematically, that would mean you're taking your RT to the power of 0. If you have the same number of moles of gas on both sides, that will give you 0 for the change in moles, which means anything to 0 is 1. Anything times 1 is itself. All right, now, homogeneous and heterogeneous. Sorry, I had a little conflict whether I'm European or English or American, apparently. I did both of them. Anyways, if you're ever curious, the American way of saying these is homogeneous and heterogeneous. The European way is homogeneous and heterogeneous. That's why you get that different thing every time. I went to a lot of conferences all around the world. Anyways, homogeneous equilibria. This involves the reactants and products that are in one phase. And so homogeneous, homo, same, means they're all in one phase. They're all same phase. You'd have everything in gases. You'd have everything in solution, something like that. Heterogeneous equilibria. This involves the reactants and products that exist in more than one phase. So this would be something like where you have solids and gases, liquids and gases. You could have solutions and gases, that sort of thing. And so right here, this is a heterogeneous equilibrium. You will notice that the previous examples you were given were actually all homogeneous equilibriums. Those were the ones we did math on so far, because I hadn't introduced a key factor when we talked about heterogeneous equilibrium. So this right here is the thermal decomposition of calcium carbonate. This is what you would see in things like an airbag. That's the solid powder goes to gas rapidly. This is how that happens. Very, very similar to this. This is also like baking soda. So if you put baking soda in something, the heat causes this thermal decomposition of calcium carbonate, creates CO2 in the baked product that makes it little pockets of air in it, which makes it light, crispy, and fluffy. Okay, so if we apply the law of mass action, this is going to give us our equilibrium expression like so. That's at least what you'd think, right? Products of reactants. Right there is your CO2, coefficient 1. Calcium oxide, coefficient 1. Calcium carbonate, coefficient 1, so power 1. However, what is the concentration of a solid? Hopefully when you were asked that, you went, what? Because you've never heard of a concentration of a solid, have you? There's densities. There's not concentration, though. And so, pure substances, these do not have concentrations. A pure substance, like a solid or a liquid, would not have a concentration. A pure substance goes to what is called unity. Unity means that it goes to 1. So you'd be putting a 1 in here and a 1 in here. You don't have to put anything because anything multiplied by 1 is the same, right? Doesn't matter. And so you do not have to put a pure substance into an equilibrium expression. And so the equilibrium does not depend on amounts of pure substances like pure solids and pure liquids. And so your K value, the C1 and C2 constants that represent these concentrations of your solid calcium oxide and calcium carbonate, these go to unity, which means that they actually are grouped up and they are already represented in your equilibrium constant. So they were in your equilibrium constant the entire time because they don't change no matter because of concentration, because they don't have concentration because they go to unity. They're solids and liquids, right? They're pure substances. All right, now, if a pure solid or pure liquid are involved in a chemical reaction, their concentrations are never included in your equilibrium expression for the reaction. Now, notice that solutions and gases, this does not apply. Solutions and gases are the ones that are always put into a chemical equilibrium expression. So let's try to write the expressions for K and Kp for these following processes. You have A, solid phosphorus pentachloride, decomposes to liquid phosphorus trichloride and chlorine gas. And then B, deep blue solid copper 2 sulfate pentahydrate is heated to drive off water vapor to form white solid copper 2 sulfate. Alright, so this is the equation for A. This is the balanced reaction. And so we're going to go ahead and try to figure out the equilibrium expression. Well, again, it is products of reactants, but your product here, which is a pure liquid, and your reactant here, which is a pure solid, do not have to be written. So that leaves you with the gas right there, which is Cl2. Notice, by the way, again, this is the coefficient. That is not the coefficient, if you forgot, which every now and then people do. So this is to the power of 1. And so what we find out is, well, our K equals the concentration of Cl2. That's it. Our K sub P would equal the partial pressure with respect to Cl2. There you go. All right. So B, right there is our balanced reaction. Notice right here, these are waters of hydration. What this means when you see this is this ionic compound has these attached to it as the solid. These are not a solution. These are not a separate compound. These are part of this ionic compound right here. And so this is one solid compound right here. Now, when you heat these up, you're going to be left with copper sulfate right there, which is again a solid. The waters of hydration will go into the gaseous form right there. All right, so we go ahead and do our equilibrium expression. And we see the only thing that is not a pure liquid or solid is this gas right here. And so K equals H2O to the power of 5, which is this right here, this coefficient. Kp would equal the partial pressure of H2O to the power of 5, its coefficient again. So use, what can we use the equilibrium constants here? This helps in predicting features of reactions, which will include determining the tendency, this does not determine speed by the way, of a reaction to occur. Notice, by the way, we are not in kinetics right now. We are not doing speed of reactions right now. We are actually looking at thermodynamics right now. So many people get the previous chapter because there is interrelationships, there's connections mixed up with this one. So chapter 12, chapter 13, 14, 15, while there are connections, they're different fundamental concepts, okay? Chapter 12 is kinetics, speed. It doesn't tell you tendency, it just tells you how fast. Chapters 13, 14, 15 are all telling you about tendency, not speed, not how fast, just tendency of reactions to occur. So whether a given set of concentrations will represent an equilibrium condition, what you can do is, if you don't know if your reaction's at equilibrium, you can figure out the concentrations and see if that gives you your equilibrium constant. If it's at the equilibrium, it has to give you the equilibrium constant. The equilibrium position that will be achieved from a given set of initial concentrations. In my opinion, this is probably the single most used feature of equilibrium constants and this entire piece of work. It's figuring out, I need this solution so I can grow these bacteria. I need this solution to act as a buffer for this medicine. I need this solution to make Coca-Cola. And then you go ahead and figure out, using the math I'm going to teach you, based on these principles that you're learning right now, how to mix that. Okay, I need to put these ingredients in based on my equilibrium constant. that will give me my equilibrium position of blah, which will be Coca-Cola, or the buffer for the medicine, or the solution that super rare bacteria you're trying to grow will grow in. Okay? That's the single most used feature of this. Uses of equilibrium constants. So here's another example of this. Let's consider this following reaction. We have species A reacting with species B, and that gives us species C and D. So Q and R will represent two different types of atoms. We have whatever, right? This could be oxygen, this could be hydrogen, I don't know. Whatever you want it to be. So let's assume our equilibrium constant is 16 here. And so again, how do we generate this equilibrium expression? Products over reactants. Okay. So this following figure is going to depict the proportions of reactants A and B in the reaction. Right there. So if we count those up, this would be our initial conditions. So assume that 5 molecules disappear of A so that the system can reach equilibrium. So we have 5 of these disappear, leaving us with 4. We have 5 of these ones disappearing because we have 1-to-1 ratio being used of our reactants to give us a remainder of 7. Now, again, for every one of these that's used, every one of these that are used, we get 1 of each of these. So that means if we have 5 of these being used, we're going to gain 5 of each of these. And so we get 5 of each of these molecules, C and D, out. Now, the new conditions, when we go ahead and use those numbers to calculate our new position, we take 5 times 5, the products, 5 times 5, divided by 4 times 7, the remaining reactants. We find out that we get an equilibrium constant. This is actually called a Q, which I'll introduce to you later. But we get a Q, our try with numbers we don't know if they're equilibrium constants or not. That is not the equilibrium constant, is it? And so what this tells you is this is not at equilibrium. Now, how could the equilibrium be achieved? Well, we would have to increase the numerator and decrease the denominator. We're too low of a number here, right? How would you make the number bigger? Well, you'd increase the numerator, decrease the denominator. And so, if we move more from the denominator to the numerator, we are going to reach equilibrium. Okay? So let's try to figure this out in a more systematic mathematical approach. By the way, this systematic mathematical approach is going to lead you into what is called ICE. Okay? So ICE problems. So here we again have our initial conditions. Okay, so how can we do this mathematically? Well, we know that anytime one of these disappears, so minus x, some number of these disappears, we have to have an equal number of these used because our reactants are a 1-to-1 ratio. We also know that if we have one of our reactant molecules disappearing, we have to make one of our product molecules as well. And so what we get is we have X number disappearing of our reactants, we have to gain X number of our products. And so we've set up a mathematical relationship. Minus X from each of these reactants will gain us plus X each of these products. Now notice we don't have any of the products at the beginning, and so 0 plus X just gives us X. And of course our initial concentration right here, 12, minus X is going to give us the remainder, right, of our reactants. So we can then plug these in to our equilibrium expression. And so we know our equilibrium constant is 16. Our products are X and X. That would be the concentrations at equilibrium. Our reactants will be the 9 minus X and 12 minus X at equilibrium then. And so what we do then is we would then have to solve for this. So we know that x is greater than 5 and it has to be less than 9. Why does it have to be less than 9? Well, 9 minus 9 would give you 0. Anything divided by 0 is not a number. It goes to infinity. Now, using trial and error, x can be determined to be 8 here. So if we just plug numbers in, we know it can't be 9, so we just go ahead and plug 8. We would find out that that would work. Okay? That would give us 16. And by the way, sometimes the easiest way to do this would be to plug numbers, especially if you're just doing a ballpark numbers. All right, but we will mention it. We'll do a problem that we actually have to do math in later. So this right here would then depict our equilibrium mixture, which is our numbers at equilibrium. Again, that would otherwise be known as your equilibrium position. So the extent of your reaction, the tendency for a reaction to occur is given by your magnitude of K. When the value of K is much larger than 1, at equilibrium, the reaction system will consist mostly of products. How do I know that? Well, K, the equilibrium expression, will always be products of reactants. If it is much larger than 1, then that means I have a lot more products than reactants. The numerator is larger. Equilibrium will lie far to the right. Again, why am I saying far to the right? Well, products are always on the right, correct? So it lies far to the right. The reaction goes essentially to completion if it is a value much, much larger than 1. Now, notice I'm saying much, much larger than 1. This means that it's a large value, okay? Like thousands, hundreds at least. Okay? And this is not true for something that's like 10. As we saw before, it does not go to essentially completion for 10. 1,000, it would go essentially to completion, okay? So when the value of K is very small, well, again, it's products over reactants, right? So if it's very small, much smaller than 1, that means that the reactants, which are in the denominator, have to be large. You have to have a law of reactants. The stuff in the numerator, which is products, has to be very small, right? And so that means you're going to favor the reactants. The system at equilibrium will mostly consist of reactants. The equilibrium position will lie far to the left, which again means over towards the reactants, which are on the left. The reaction does not occur to any significant extent. If you were to put reactants together, they would stay reactants. Very little of them would become products. The size of K and time to reach the equilibrium, these are not directly related. So your time depends on the rate of the reaction. Remember, that depends on the things like activation energy. So the size of your activation energy is your major concern when you're talking about the speed of reaction. The size of K is determined by thermodynamic factors. So this is going to be thermodynamics. This is your energy difference between products and reactants. Is the reaction spontaneous or not? That's what you're being shown. All right, I mentioned Q before. If you put any conditions that are not equilibrium conditions into that equilibrium expression, that law of mass action that we saw before, that's no longer going to be an equilibrium expression if it's not at equilibrium. So, what you have here, you have a reaction quotient. This can be used for any conditions. So this is used to determine the direction of movement towards equilibrium when all the initial concentrations are non-zero. By the way, if you have some of the concentrations at 0, then you can't have the reaction going away from those concentrations, right? Because you don't have anything to react. All right, this is obtained by applying your law of mass action. Instead of using your equilibrium concentrations, you'll use your initial concentrations. You'll write up your law of mass action just like before, just like you would for an equilibrium expression. but it will be a reaction quotient instead. And instead of putting K, you will put Q. Notice the Q sounds a little like K, and frankly, they ran out of symbols, so it is Q. Also, Q works very nicely because typically you're using this to question whether you are going to equilibrium or not. By the way, if your value of Q equals your equilibrium constant, then it is your equilibrium constant. You are at equilibrium. Congratulations. So right here we see the relationship between the reaction quotient and equilibrium constant. So again, if Q equals K, you're at equilibrium, okay? That is equilibrium. That's it. All right, so if Q is larger than K, the system has too much product, and you will shift towards reactant. You will consume product to make more reactant until you reach equilibrium. Now again, this doesn't tell you how fast it will happen, but eventually you will go towards equilibrium. If your Q is less than K, then the system has too much reactant. You will consume reactant to make more product and shift the reaction to the right towards product, which will give you the system at equilibrium eventually. So for the synthesis of ammonia at 500 degrees Celsius, the equilibrium constant is 6 times 10 to the negative second. Predict the direction in which the system will shift to reach the equilibrium in the following case. And so right here you have your initial concentrations. Remember that 0 means at time 0 or initial. This is just one way you can write initial. You can of course put I for initial. And most people, many other books and many other chemists would put I here, you put 0. Both mean the same thing. Every chemist will know that, okay? Every scientist should know that. If you run across one that doesn't, please explain it to them. All right. At equilibrium, this will have a small e next to it, by the way. All right, so what we're going to end up doing here is we're going to end up doing a reaction quotient. This is going to be just like as if we were doing a equilibrium constant with an equilibrium expression, but again, with a reaction quotient, we can go ahead and plug in these values right here, which are our initial concentrations. So let's go ahead and get to it. So we get our reaction quotient. Again, we use our equilibrium reaction that we were given there. We plug in products on the top, reactants on the bottom. These powers are again their coefficients, just like before. Just remember, it is for any conditions. We don't need it to be at equilibrium. We're trying to find out if it is at equilibrium, in fact. Okay, so we plug the values in, we do the math. Be very careful about doing these maths. It's very easy to screw up. And you get a 1.3 times 10 to the 7. We know that K is, which is our equilibrium constant, is 6 times 10 to the negative 2. So in this case, Q is much greater than K, vastly more. And so we know right now we have way too much product. We need less product, more reactants. So to attain the equilibrium, the concentration of the products must decrease. The concentration of the reactants, therefore, must be increased. So the system in this case is going to shift from products to reactants. And therefore the reaction is going to go towards the left, towards making these species right here, the N2 and H2. All right, so let's go ahead and calculate equilibrium pressures and concentrations. So typical equilibrium problems are going to involve calculating what the concentrations would be at equilibrium given a equilibrium constant. So to determine equilibrium concentrations of reactants and products, value of the equilibrium constant and initial concentrations will be provided. Mathematically, for a full calculation where we're using these first introductory equilibrium problems, this can be a fairly complicated problem mathematically. So you want to develop strategies to simplify this, to break it into pieces so you can do easy, small pieces of it instead of having to do a large, difficult problem. So what we're going to do here is we're going to try it out. So right here we have this reaction. So dinitrogen tetroxide. It was in the liquid state, used as one of the fuels on the lunar lander for the NASA Apollo missions. In the gas phase, it decomposes to gaseous nitrogen dioxide, like so. And so we have this equilibrium here. Let's consider an experiment in which gaseous N2O2 was placed in a flask, and we allowed this to reach equilibrium at a temperature where the Kp equals 0.133. At equilibrium, the pressure of N2O4 was found to be 2.71 atmospheres. Calculate the equilibrium pressure of NO2. Okay, so our equilibrium pressures of our gases NO2 and N2O, they have to satisfy this equilibrium expression. And so we can write our equilibrium expression. And remember, we know Kp, we were given that. And so we write our equilibrium expression from that reaction. Again, it's products over reactants to the power of the coefficient. And so that will be equal to the value we were given, which is 0.133. So then we can solve for the equilibrium pressure of NO2. And so we solve for the NO2 to get it on one side. That leaves us the two values we were given in the previous slide. We plug those values in, 0.133, which is our Kp, 2.71, which is our partial pressure of N2O4 at equilibrium, and this gives us our equilibrium concentration of 0.360 once we take that square root. Okay, so we will have our equilibrium partial pressure of NO2. And so our equilibrium partial pressure is the square root of 0.360, which is what we got from the previous part, and that gives us 0.600, which would be in atmospheres if you're curious, which I forgot to put in this slide. So let's try another take on this problem. So at certain temperature, a 1 liter flask initially contained 0.298 moles of PCl3 and 8.70 times 10 to the negative 3 moles of PCl5. After the system had reached equilibrium, 2.00 times 10 to the negative 3 moles of Cl2 was found in the flask. So gaseous PCl5 right here, this is going to decompose according to this reaction. So to PCl3 and Cl2. So let's go ahead and calculate the equilibrium concentrations of all species and the value of K. So again, look at our starting conditions. We have moles here, but they're in a 1 liter flask. That means all of these are already in molarity, right? They'd just be over 1 liter, which is the same numbers. So we don't have to do any real math. We just divide them by 1 liter. Congratulations, you have molarity. Again, this is in 1 liter flask, so again, the overall volume is again 1 liter. That means that this right here, again, you get to do it divided by 1 liter, which gives us a very nice problem. That is 2.00 times 10 to the negative 3 molarity. Okay, so one of the things you should take note for, and this is just good problem solving 101, is you should always build up what you have, what you need, and how to get there. Okay, that's just good problem solving. So what we have here is we don't really care about the temperature. That doesn't matter. This doesn't actually matter. All that matters is we know that these numbers are the same as they would be for their molarity. And so we have this initially containing this amount of PCl3, which is this right here, this amount of PCl5, which is this right here. And so those are our initial concentrations of these two values. At the initial, we do not have any of this Cl2. None of it's mentioned, so we don't have it. And so we have 0 molarity of Cl2 initially. At equilibrium, we have this value for the Cl2. We do not have a value of K, and we do not have our concentrations of our other species at equilibrium. So what we have to do now is the first thing we should always do for all of these equilibrium problems is just go ahead and generate an equilibrium expression. And so we go ahead and make our equilibrium expression, products of reactants, just like before. So how do we find the value of K? Well, you have to calculate the equilibrium expressions for all the species, don't you? You then you can substitute the derived quantities into your equilibrium expression, and then you can do your math and get K. So let's figure out our initial concentrations. So we know that initially we have Cl2 as 0, we have this molarity of PCl3, and this molarity of PCl5. So how do we get our equilibrium conditions? Well, we do this through the reaction, don't we? So our reaction, we have made during this reaction that equilibrium amount of Cl2. So if we have made 2 times 10 to the negative 3 moles of Cl2, well, for every mole of Cl2 we make, we have to make the exact same number of moles of PCl3. How do we know that? That's what this reaction tells us, is that for every one of these we use, we make one of these and one of these. That's what that says. If you don't know that and you are going, where is this coming from? Seriously, you need very badly to review. This is essentially one of the primary concepts you learned all of last semester. So, yes, please do. Anyways, so again, you have to have the same at equilibrium made of this PCl3. This then would be the net amount of PCl5 that we make at equilibrium right here. So PCl5 has to have used this same amount. So this is minus. This is being removed. This is being used up. Now, some people would ask me a question along the lines of, Dr. Clausen, how do we know that this is being used and instead we don't go ahead and use these and make that? And the answer to that is that we start with 0 of this. Can you make hot dogs if you don't have any hot dogs? Can you make hamburgers if you don't have any hamburgers? No, you can't make any. Because you have 0 of this, we know we have to have made this. Okay? So we already know the signs. We know the direction it's going. It has to make Cl2. We can't make PCl5 in this reaction with the initial conditions. So we go ahead and apply these values to our initial concentrations. Remember, this is the amount being made, but we didn't start with any Cl2. That's why we know we made that amount, as they gave us our equilibrium condition for this, our equilibrium amount. However, we did start with some PCl3, didn't we? And we started with some PCl5. So we're going to have to take that initial concentration for this, subtract off the amount we used, and for this we'll have to add on the amount we used. So again, we started with 0 Cl2. And that means all of the stuff we made is the amount we have at equilibrium. For the PCl3, we started with 0.298 molarity. We made 2 times 10 to the negative 3 moles over 1 liter, which is the amount of molarity. And so that means we end up at equilibrium with 0.3 molarity. Now, for the PCl5, we had this amount initially. We used up 2 times 10 to the negative 3. And that will give us our equilibrium amount, which is 6.7 times 10 to the negative 3. Note, by the way, that you cannot use more than you have. if you get a negative concentration for whatever reason, that is impossible. There is no such thing as a negative amount of something. Okay? This is not antimatter, which isn't even a negative amount. I'm just joking. But this is, you can't have negative amounts. There's no negative overall moles. You can't have negative $5. You can't have negative 5 moles of something, okay? There is no universal bank of moles. All right, now let's determine the value of K. So substitute the equilibrium concentrations into your equilibrium expression. And once we substitute those in, we'll just go ahead and do the math, multiply, divide, and that will give us our value for K, which is right there. And congratulations. Hopefully you attempt this problem and you should get the same number. All right, so let's assume that the reaction for the formation of gaseous hydrogen fluoride from hydrogen and fluorine has an equilibrium constant of 1.15 times 10 to the second at a certain temperature. In a particular experiment, 3 moles of each of the components were added to a 1.5 liter flask. Let's calculate the equilibrium concentrations of all these species. Alright, so your balanced equation is this. That's H2 plus F2 yields HF. Your equilibrium expression, of course, products over reactants. Remember, K is our equilibrium constant. We have been given a value for that, which is right here. That will be equal to our equilibrium expression right there. Your initial concentrations are as such. This is why, by the way, these are often called ICE problems. Every time you do these problems, they're almost always going to break down to listing off your initial concentration, I, figuring out your changes, C, and then calculating your equilibrium concentrations, E, from those. If you would like, I actually, I can't do this worth a damn on my computer. It just does not turn out right, and it just becomes more confusing. But in many ways, the easiest way to do these problems is actually by taking this equation right here, writing it on a piece of paper, writing I, C, E next to it, and then write your initial concentrations here, your changes here, and then your equilibrium concentrations here. And then I typically have people go ahead and write their K's up here above it. And that organizes it in a very nice way so you can just know where to look for everything. Makes the problem a lot faster when you start to work it out. It also makes it much more formulaic, which many people find comforting. Okay, so the initial concentrations are all the same because we put the same amount in for all of them. So we put in 3 moles for all of them. This is in a 1.5 liter flask, so the concentrations are 2 molarity for each of these. So the concentration of HF, 2 molarity. H2, 2 molarity. You get the point. Note, by the way, you cannot do these equilibrium expressions in moles, okay? They are in molarity. They're in concentrations, or a Kp would be in partial pressure. None of them are in moles. So your value of Q would be as such. This is how you can tell which direction this reaction would be heading towards. And so, right here, we have Q. We plug in our initial concentrations of each of these, right there, and that is going to give us a Q of 1. So Q here is much less than K, which we were given. Remember, up here, right there. And so we have to be going towards, we have to shift towards the right to reach equilibrium, which means we are shifting so that we have more product. We will consume reactants, making product. So to determine the change in concentration is then necessary. We have to define that change. And the easiest way to do this is to put in X. You're comfortable, hopefully, with the term X to define some quantity, right? So it's a variable quantity. It is something we want to find. So we go ahead and make the change in the number of moles, or the change in the molarity, be x. So let's go ahead and take x, and that will be the amount of H2 that's consumed to reach equilibrium. This same amount will then be proportionally the amount of F2 that will also be consumed, and it'll be the amount of HF that will be formed. So we use the stoichiometry of this reaction to get that for every x, so x amount of H2 that's consumed, we will also, let's go back up to the reaction, we will also consume the same amount of F2. You see that's 1-to-1 ratio. So if we consume x moles of this, we will consume x moles of that. And for every x amount we consume of these reactants, we have to make 2x, twice as much. So 2x amount of the HF. All right, so right there we see the example. This would be the change of the molarities. We will consume x from each of these. We will make 2x of this. So right here we see our initial change equilibrium. It's flipped from the table that I would normally have you guys write. So I'm doing them across the top. So the initial concentrations were these, and that's what we figured out before. This right here is the change in each of these molarities. Again, this is minus x because we consume one of these, we will consume one of these, and we will make 2 of these. And so this is plus 2x. Remember, that is just the stoichiometry. You don't have to think too far in it. Many people try to dive really far into this and think that's very complicated, and I have to worry about, oh my god, this is also the exponent, and why is this the exponent, and it's also the x's here, and you don't, okay? They're both from the stoichiometry. They are not directly related. You don't have to worry about it. All it is just the stoichiometry, okay? So this is just minus x here, and then yes, your equilibrium expression will then be a different thing that it does not have to be related, okay? You don't have to worry about why the equilibrium expression and why these right here both have 2's, okay? You just have to follow along, do the procedure step by step. That's why we break these type of problems down into steps. Is if we try to do them all as one piece, they can become quite overwhelming. Okay, so again, well, we have the initial, we have the change, so the equilibrium will be the initial plus that change. And so that is 2 minus x. This will be 2 minus x. This one will be 2 plus 2x. There you go. All right, we have our equilibrium concentrations right here. Those are those expressions right there. Those are little equations. And so we are plug those in. By the way, here's how it should look if you did this in the ICE table configuration like I was recommending before. This shorthand table notation is much, much, much easier for students to deal with. I really find that if students use this and are pretty diligent about using this, it usually doubles to triples their ability to do these problems. Okay, it is a huge help in students doing these problems. So again, ICE, you can remember ICE problem, ICE baby, if you will. And so ICE, initial change equilibrium. You will take these equilibrium concentrations and you will put them in your equilibrium expression, and then you will calculate out x. So you will go ahead and substitute those in to your equilibrium expression, which is right here. So we substitute that in, we substitute this, and these are the same, so this is just to the second. It's literally just 2 minus x times 2 minus x. And that's what the square is right there. So this one actually can be simplified a lot and made to be a much easier problem. This is to the second, this is to the second, so that means this whole thing is actually to the second. And so we can just take the square root of this side and this side, like so. So we take square root of here, square root here cancels out those to the seconds. And so we can then just solve in a much easier way. Go ahead and calculate that. Then we're going to multiply this over, and then we solve for x. And there's your solve for x. By the way, actually try this, okay? I know that, yes, I have mastering and it guides you through it. What I find though is mastering makes you students helpless. It tends to make you depend on it, which then makes you helpless if you actually have to do a problem without it. Which is not good. That's not what I want for my students. I want my students to actually know what they're doing, be competent, so when you get out in the world, you don't depend on somebody else. You can do your own work. And you can, be successful in life and not just be a little parrot that parrots out whatever mastering says. So please actually attempt these problems without depending on a guide that breaks down all the math steps for you, okay? That's not a good thing if you can't do these problems if you can't do the math without a guide showing you how to do the math beforehand. That's a very bad thing. So the equilibrium concentrations will be, we just take that value of x, we go ahead and plug it in to our previous table. And so we had 2 minus x. So we plug in our value of x, and that means that the concentration of H2 and F2 are 0.472 molarity. The concentration of HF, well again, this will be 2x, so 5.056 molarity. And yes, that'll give us our concentrations. So a good procedure is always to do a reality check. If it's not a just 100% easy problem, if you're not absolutely sure, you should always go ahead and double check. Does my answer make sense? So you check these values by substituting them into the equilibrium expression. This should give you your same value of K. Literally, you take the equilibrium expression and put these values back into it. If it gives you K, yes, it is proper. It's good. You did a good job. You solved the problem correctly. Excellent. Great job. So this is that problem-solving strategy that I've taken you through. Okay. This is just a list of it. If you forgot how to do it and want to have a little list you can sort of have in the back of your head, here it is. All right, so let's calculate some equilibrium pressures. Let's assume the gaseous hydrogen iodide is synthesized from hydrogen gas and iodine vapor at a temperature where the equilibrium constant is 1 times 10 to the second. Suppose HI is this atmosphere, H2 is this, and I2 is this. They are mixed in a 2-liter flask, or 5-liter flask, excuse me. Calculate the equilibrium pressures of all species. So mixed in a flask means that these are reactants. This is initial. You put them together, you put them in a flask, you mixed them. Yeah. So you now need to figure out the equilibrium pressures. You've been given the constant, the equilibrium constant. You've been given the initial pressures. This is going to be the same problem again. All of these equilibrium problems really are the same ones over and over. Yeah, you're going to find that it is extremely similar, and they are horrifically boring for me to do because it is essentially the same problem over and over and over. Okay, so that's your reaction right there. So we then will make our equilibrium expression. Again, products of reactants, coefficient. All right, we've been given this value, so we go ahead and plug that value in right there. That is the Kp right there. All right, so we have our initial pressures that were provided. we can go ahead and calculate a Q that will give us a direction we're supposed to go for this reaction. And so we go ahead and plug these initial values in to our expression. This will give us Q, the direction we're supposed to head. And so right here we plug this in, and we get 5 times 10 to the third. So Q in this case is greater than K. What that means is the system will have to shift to the left to reach equilibrium. Another way of thinking about that is if Q is greater than K, well, you have to remove some of the numerator, which is product, right? You have to increase the denominator, which is the reactants. And so you have to get rid of product to make reactant. So use pressures for a gas phase system at constant temperature and volume. These pressures will be directly proportional to the number of moles. So this is a constant if you have a constant temperature and volume. Notice that R is a constant. If this is constant and this is constant, it's all constant. So let X be the change in your pressure in atmospheres of H2. As your system shifts towards the left in your reaction, this will lead to the following equilibrium pressures. Again, your ICE table. Take your reaction, list ICE to the left, make sure you have space under your different species, okay? I would do it fairly far to the left so you have some space. You don't have to write it all out. I would normally just put ICE here. List your initial concentrations like so. Then you will figure out your changes based on the stoichiometry. And so right now we know that we have to use up this to make reactants. We have to use a product to make reactants. We got that from our reaction quotient. And so this says that we have to use up, this number 2 here, says that we have to use up 2 of these for every one of these we make. And so we use 2 minus 2x. We're using 2 of these. We are making then, for every 2 of these we we make 1 of these. So that's plus x. And we make 1 of these, which is plus x. And so we now have our changes. The next thing we're going to do is we're going to figure out our equilibrium concentrations. Well, equilibrium is just the initial plus the change. And so the equilibrium value is here, the initial plus our change. Right here we have our initial plus our change. Here we have our initial plus our change. Notice our change is negative in this case, which means that the plus, if you will, put quotation marks, turns negative, right? Because that is using it up. Okay, so we are going to go ahead and plug those equilibrium concentrations into our equilibrium expression, which is what you're seeing right here. So these are our equilibrium concentrations being plugged into our equilibrium expression. So in this case, this one is going to be fairly mathematically complex. I'm sorry to say that you remember that quadratic equation you should have learned back in high school and then reviewed when you took the math. That was the prerequisite for this course. Yes. Well, it's back, okay? I would highly recommend that you just go ahead and memorize that quadratic equation again. Whenever you start an exam from now on, that in these, for this chapter, chapter 13, really you won't need it for any other chapter, but chapter 13. And the final. So when you start an exam, there's something that's called loading and unloading. It's a test-taking strategy that's very common, and especially in places where standardized tests are very valued. And what it is before the exam starts and you're studying, right before the exam starts, you load the equations into your head. And so literally the 10 minutes, 5 minutes leading up to the exam, you'd sit there with flip cards and memorize the equations. That's it. Okay? You'd sit there repeatedly writing them out. All right? And then Once the exam starts, you're going to have your scratch paper. Once the exam starts and you've done all the calibrations and everything, you're ready to go, you'll go ahead and just sit there while the first question's taken away, and you'll write down all those equations on your scrap paper. And that's it. Okay? You unload them right away, so then when you get to, halfway through the exam, you're tired, you don't have to remember them anymore. You already had it on your scrap paper. You don't have to try to come up with it again, because you get tired and your brain will fail you. Okay? So this would be one I would recommend loading. Again, this right here, what you're going to do is you will solve this down so that you have a set of x squared plus x plus a number, right? And that will be the value in front of x squared will be your a, the value in front of x will be b, and c will be your number without an x. And that will give you these. That's what you get once you solve for this. I would double check that you can do this. That is from this again. See, that's there, and right there. Notice what we've done is we've solved this. We've solved the KP. We've gotten everything to one side and left 0 on the other side. Now, if you remember your quadratic formula, you're going to be given, you can get two values for it. You have a plus and minus. So there's a big hint. What you want to do is, first off, you can't have negative pressures. You can't have negative concentrations, right? So any negative value you get from a quadratic formula is automatically wrong. The other hint is when you do this, the correct value for x is going to be this, 3.55 times 10 to the negative 2 atmospheres. The largest value you can have for this negative right here, this minus 2x, that can only be equal to this value, right? You can't have a negative concentration once you do this math here, okay? So that's another hint on what you should take for your quadratic formula. So the equilibrium pressure can now be calculated using this value of x. So the pressure of HI, again, that was the equilibrium value that we saw at the bottom of our table. We plug that value right here in, and we get 4.29 times 10 to the negative 1 atmospheres. We do that for H2. We get that value right there. See, there's our value from there. And we do that for I2 as well. And we get this value. And ta-da, you have completed the problem. You have gotten the equilibrium pressures. So let's go ahead and double check. Let's do a little reality check. Let's put in our equilibrium pressures back into our problem. We go ahead and do it. We get into our equilibrium expression. And we get a value of 99.9 for our Kp. Does this agree with our value of 100? That's 100 right there. Yeah, that's within calculation errors. That's because we rounded some values here. That's it. So what about systems that have small equilibrium constants? So remember where I said the more information I give you, the easier the problems are? This is a great place where working smarter means working much easier. Okay? Alright, so here we're going to look at a small equilibrium, and this is going to give you more information that you can then assume things and make your problems mathematically easier. So here we have the decomposition of gaseous NaCl. Really, all of this information here is just telling you it's at this temperature, so it's at a single temperature, and it's this reaction, okay? That's what you're really reading here. The equilibrium constant is this value here, so now we have a value of K for later on. The following steps determine the equilibrium concentrations, blah, blah, blah. When 1 mole of NaCl is placed in this flask, our balanced equation is right here. So we have 1 mole put in a 2-liter flask. And so that means we have 0.5 molarity, don't we? And so the first thing we do, we write out our equilibrium expression based on this balanced equation right here. And this was equal to that value of K we were given. The initial concentrations then are, well, we started off with this. This is the only one we mentioned. We don't have any of the other two species, which are our products in every sense of the word. Now, right here, we have 1 mole for 2 liters, giving us 0.5 molarity. All right, so we can go ahead and set this up. There's no products initially. We don't have to bother with a Q or anything like that. This system has to go towards, well, where there's no products. So it has to make product and it has to use up reactant. So again, we can use X to let that be the change in concentration. So this will be the change in concentration of Cl2 is 1x. We'll make 1x because we make one of these. This will be 2x because it's 2 of these will be made for every one of these. And this right here will be 2x being consumed. So we go ahead and tabulate that into our ICE table. And again, that is 0.5 minus 2x for the equilibrium concentration. This right here will be 0 plus 2x, which is 2x. We don't have to worry about the 0. This will be, you'll make 1x. So let's think about this a little bit though. So our equilibrium concentrations, when we do this, we substitute these equilibrium concentrations in. And we look at this expression. So we have a 1.6 times 10 to the negative 5, right? That's a pretty dang small number. That's a 0.00016. That's very small. And so we look here. Well, this number has to be somewhat proportional to this right here, doesn't it? Because this is at best 0.5, because we couldn't have a 0. So that means that this right here is much larger than x, because we know x has to be a very small number, like this k is. So if we have a very small number for k, that means x is always going to be a fairly small number if we have a value of x up here. And 0.5 down here is much larger than this value of x could be. And so we can actually make a little bit of a shortcut. So our value of k is so small that we know any change, any value of x, is very small. It's not going to be very meaningful. It's going to be a relatively insignificant amount as compared to 0.5. And so what that means is, let's think about math a little bit, okay? If I subtract 0.000002 off of 0.5, I'm just going to end up rounding it back up to 0.5 when I put it in the calculator, aren't I? And so this is proportional to 0.5. We can eliminate that minus 2x. We don't need to do it, because this is addition and subtraction. The addition and subtraction of a very small number to a larger number means that addition and subtraction is somewhat meaningless. It's insignificant. Notice I say addition and subtraction. Multiplication is different. Multiplying right up here, small numbers, gives you smaller numbers, okay? It doesn't matter whether these are big numbers in here or not. Multiplying by a small number, even if it's a big number, still gives you a big effect, okay? It's only where we have addition and subtraction, like down here, that we can go ahead and assume that this is meaningless. And so what we say here is that this expression right here, which we got before, is proportional to just taking 0.5 in the denominator. That means we just got rid of this 2x here. See that? Now, the great and wonderful thing about that is now we don't have to do the quadratic formula. We can skip it. Woo! Yay! That's a huge amount of work that we're just, bam, gone. And so we take this, we do the work. Well, this is 2 to the second 4. This is x squared, and then times x, so x to the third. This right here will be 0.5 to the second, because we got rid of this, because again, x is going to be a small number. It's insignificant when you subtract it from a 0.5. Okay, so we have assumed that, right? Now, if we solve for that x cubed, then we get 1 times 10 to the negative 2. So we actually have to go back and we have to test, was this a valid assumption? So whenever you make assumptions, you always should check reality, okay? Test if it's a valid assumption. And so what you can do then is you can take that x, you can substitute it in, and look, is 0.5 minus 2x, is that an insignificant change? So we go ahead and do that. Minus 2 times our value of x right here. And that is 0.48. So yes, it is. That is a rounding error level number. It's such a small number, it really doesn't have any significance here. And so that is fine. That will have little effect on our outcome, and we can go ahead and use that assumed value of x. And so we use that approximate value of x to calculate our equilibrium concentrations, just like before. And we put that in. Well, it gives us a number around 0.50. This right here is 2x, so we just take 2 times our value of x, and we get this number here for our molarity of NO. This is x, so we just take our number of x, there you go, and that is the value of Cl2 at equilibrium. So it's always a great idea to go ahead and do a reality check, especially if you're doing this for something important, like say your grade on a test, or if you did this in a lab setting where your job depends on it, or the product batch depends on it. All right, so reality check for this would always be plugging this back into equilibrium expression. Do you get your equilibrium constant? So we plug these values in. They give us the value of k as being the exact same. And so yes, that was fantastic. Everything worked out. We have checked reality and it worked. All right, you have learned how to treat systems that have small equilibrium constants by making approximations to simplify our math. What if this system has a very large equilibrium constant? What can you do to simplify the math for this case? So think about something like 1.6 times 10 to the 5th, and then try to work a problem with it. So what could you do? Well, let's go back to this example, right? So here, up here, let's look at this. What if this, instead of being a 1/10,000th number, this was a very small number before, what if it was a huge number? So what we would see here is that if this was a huge number, then x would be big, right? It would be very, very, very big. And so what we can do then is x actually is going to start overshadowing this value right here. And so this is going to go to essentially 0 here, won't it? And we know this is going to go to essentially completion. So we will essentially get all of our reactant converting to product. And that would simplify the problem because you can just convert all of it to product if we have a very, very large equilibrium constant. Why can't you do this for a moderate equilibrium value like 1.6, something, kind of moderate, not really big or small? Well, you don't have an extremely large or small number, right? All your numbers are moderate, so they're all meaningful. You can't overwhelm any single number. Okay, so Le Chatelier, I always pronounce his name because I will never get it correct French pronunciation. He has developed a principle. He was a a chemist, if you will. They weren't really called chemists. Natural philosopher was the correct terminology back in the day. And he came up with an easy way of envisioning these equilibriums and how they react to different stimuli. And so Le Chatelier's principle, if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. This will help a qualitative prediction of the effects of your change in concentration. We already discussed a quantitative, that is using the reaction quotient Q versus the K equilibrium constant. So again, this will be a qualitative. We're just in general, what direction is this going to go? So this is going to account for the changes in concentrations, changes in pressure, and changes in temperature on different system equilibrium. So let's go ahead and try it out a little bit. Let's consider the synthesis of ammonia. Suppose there's an equilibrium position described by these concentrations. So let's assume that 1 mole per liter is then injected of the N2 into the system. So let's predict the result. We could predict, of course, the result using calculating the value of Q, comparing it to K, of course. And so we would do that. Let's try that out. Again, we add that value. We get this as then our concentration. And these are then labeled as our initial concentrations. So our system will no longer be at equilibrium, right? And now we have more of the N2 reactant. And so when we determine our Q, we have to use these new values. That's going to give us this value of Q, which is 1.7 times 10 to the negative 2. So we have our value of K then, which was our equilibrium concentrations in our equilibrium expression. And that is this value right here. We would then compare these. So is Q larger or smaller than K? Well, Q is smaller than K because the concentration of N2 was increased. The system thus will shift to the right, and that will become its new equilibrium position. Again, shifting to the right means we will use up reactants to make product. Now, you probably could have figured that out though, right? You probably could have instinctively said, if I add more reactant into an equilibrium, it would shift away from reactants towards products. And that was Le Chatelier's principle, actually. So what you're looking for is the easiest way to deal with Le Chatelier's principle and to think about equilibriums. In my opinion, is always either a seesaw or a bottle of water. So when you have the bottle of water flat on your desk, the water will be distributed equally. And that's an equilibrium, okay? So what happens then if you put more water on the left side, which would be reactants? Well, that will flow towards the right, won't it? And so you will end up, if you give it more reactants, you will push it towards products. What happens if you put water on the right side? Well, it'll flow towards the left, which is the reactants. So again, if you give it more products, it's going to push towards reactants or shift left. All right, so the seesaw, by the way, would be like if you put more weight on the seesaw, then it's going to cause the seesaw, if you put more weight on the left side of the seesaw, it will cause the right side to go up, right? And so it's pushing right. If you put more weight on the right side, the left side will go up, so it's pushing left. You get the analogy, hopefully. This is a simple visual representation you can use to quickly identify Le Chatelier's principle. Le Chatelier's principle is actually quite easy to predict as long as you use these sort of visual representations. All right, so this is just a diagram that shows you that same information in a probably unnecessarily complicated way, but it is in your book. All it's showing you is you have an equilibrium. You add N2. Your N2 is now greater amounts. So it will consume N2, making the NH3 to reform a new equilibrium level. This will not have the same position or concentrations as your previous equilibrium, but it will have the same equilibrium constant. So this is an alternative definition for Le Chatelier's principle. If a component is added to a reaction system at equilibrium, the equilibrium position will shift in the direction that lowers the concentration of that component. Now, we've so far just talked about concentrations. I will get into the others next. If a component is removed, the opposite effect occurs. Now, system equilibrium exists at constant temperature and pressure, or constant temperature and volumes. You should keep that in mind. That actually can affect, if you change all three factors, that will affect system equilibriums in very hard to predict ways. So, arsenic, this can be extracted from its ores by first reacting the ore with oxygen. This is actually called roasting. This will form arsenic As4O6, which is then reduced using carbon. And so then you'd put carbon, charcoal, essentially, in with this. This would reduce it to the arsenic, pure arsenic form. Anyways, that's the reaction we're looking at here. We're going to use Le Chatelier's principle to predict the direction you're moving. This is a very typical thing to do in industry, by the way. Many of the people working on the floor, of course, don't know this, but there's always at least one chemist in most of these facilities who is overseeing and helping to provide information to make the process more efficient. And so let's say you're not getting as much As4 out as you predicted, that you thought you would from your bed, your roasting pit, if you will. Anyways, how can I improve it? Well, you can use Le Chatelier's principle to say, hey, put more of this in. Okay? All right, so let's predict the direction of the shift of the equilibrium position in response to each of these following changes in condition. So let's say we ended up getting an additional of carbon monoxide into this. What is going to happen? Let's say we had an addition or removal of carbon or tetraarsenic hexoxide. Well, we weren't shoveling in carbon. We weren't shoveling in the arsenic hexoxide. Excuse me. What's going to happen? C. Removal of the gaseous arsenic. So we had a removal of our gaseous arsenic. We have a piping system that removes that. What's going to happen to this? Okay, so A, we use Le Chatelier's principle. If we have the addition of carbon monoxide, that is going to be increasing this product amount. So, again, we are pushing up on this, we're increasing this amount. That's going to cause a shift left towards reactants, right? And so if we have a buildup of carbon monoxide, we will actually have less going into product. More of this will actually go into reactants. We'll actually produce less and less of our As4. So, for example, if we had a venting system, or if we had a buildup for some reason of carbon monoxide in this industry, in this industrial environment, we would actually end up producing less and less product over time, and it become less and less efficient. Here, I'm just going to stay on this pages right here, and then you can flip down to those who want to learn the answer after I give you the answers here. So the addition or removal of carbon or tetraarsenic hexoxide. Excuse me. I gotta drink of water. All right. So addition or removal, those are two different ideas, right? So if we have any addition of these, that will push the equilibrium towards products. So, for example, in most industrial reactors, you will continuously shovel in reactants to push the reaction towards products. And that's actually using Le Chatelier's principle. That's what they're taking advantage of. A removal of these would obviously cause the products to shift left, right? We would, instead of making more products, we would actually start making more reactants if we started removing reactants. So that would be called shift left, shifting towards reactants. If you add more reactants, you shift right, shifting towards products. Removal of gaseous arsenic, AS4. So if we continuously remove this, what is that going to do? Well, that will keep shifting this right towards products. That means you'll keep making more and more of this. Okay? And that's actually the two ways how you get industrial reactors, actually. You keep removing the product and, selling it to people. And you keep adding reactant so that the reaction equilibrium keeps pushing towards your product and you get more and more of it. And by the way, that's why shutting down operations in most of these industrial reactors doesn't actually work out like people think. Like, if you want to save 50% of your money, you can't just shut down 50% production. That's not how it works. Saving 50% of your money usually means shutting down like 80% production. It's not linear in any way whatsoever. All right, now, the effect of a change in pressure. So methods used to change the pressure of a reaction system with gaseous components. You can add or remove a gaseous reactant or product. If you add a gaseous reactant or product, that will change the pressure, right? If you remove it, it will lower the pressure. You can add an inert gas, so one that's not involved in the reaction. The more gas you have, the greater the pressure you'll have. You can change the volume of the container. You guys all probably know this. You've taken a water bottle probably and tried squeezing it. If you squeeze a water ball, thus changing the volume, lowering the volume of the container, you will increase the pressure. If you increase the volume of the container, you will lower the pressure. Which, of course, is if you ever take a water ball, it's empty, squeeze it down, put it on your palm, let it try to reinflate, it'll suck onto you because it is low pressure, is lower pressure than the atmosphere around you. Okay, so the effects of a change in pressure, some of the key points. The addition of an inert gas will increase the total pressure. This does not affect the concentrations or partial pressures of the reactants or the products. So when the volume of the container holding a gaseous solution is reduced, the system responds by reducing its own volume. The total number of gaseous molecules is reduced then. So we can rearrange this ideal gas law to give us this. This gives us a representation of how pressure and volume are related. So we notice at a constant temperature and pressure that the volume is actually directly proportional then to N moles. And so if you have more moles, they're going to take more volume, right? If you have less moles, you're going to take up less volume. And so your equilibrium position will shift towards the sides of the reaction that involves the smaller number of gaseous molecules in the balanced equation as you reduce the volume. Okay, so let's try it out. Right here we have our great N2 plus H2 gives us NH3, right? And so reactants, which are the N2H2, those have more moles than our products. And so if we reduce our volume, what we're going to see is as we reduce our volume, we're going to shift the equilibrium towards the less moles of gas, which is the NH3. And we will actually shift it away from the N2 and H2, which have more moles of gas, and thus are less favorable for a smaller volume. And so reducing this volume, right here, just pushing on the plate, will actually shift your equilibrium towards NH3, making more NH3, and away from N2 and H2. And so you have less N2 and H2 at equilibrium, your new equilibrium for that volume. So you and a friend are studying for a chemistry exam. What if your friend says adding an inert gas to a system of gaseous components at equilibrium never changes the equilibrium position? How do you explain to your friend that this holds true for a system at constant volume, but is not necessarily true for a system at constant pressure? When would it hold true for a system at constant pressure? Okay, uh, this would actually be a great opportunity to actually try thinking on this on your own. Um, Let me go ahead and go through that, actually. Let me know if you want me to answer this, but honestly, it would be a great opportunity to try thinking about this on. It's just the same relationship up here, okay? This is we have everything you need right here. Okay, so let's try this interactive example again. This time with a slight shift, a slight difference, if you will. Predict the shift in equilibrium position that will occur during the preparation of liquid phosphorus trichloride. And so we have phosphorus reacting with chlorine. This gives us PCl3. Let's assume that the volume is reduced in this. All right, so right here we have a solid, we have a gas, we have a liquid. So the P4 and PCl3 are pure solid and pure liquid. The one we need to consider here is only the effect of the change in volume on Cl2. So Cl2 is our only gas here. So if the volume is decreased, the position of the equilibrium will shift towards the right. Because, again, volume decreased, we want to decrease the number of moles of gaseous molecules. That means that we need to convert the gas here to our liquid form, thus taking up less volume. So remember, reduction in volume means a reduction in the number of moles in gas. In this case, we try to go to the products or shift right. Again, your reactant side is the only one that actually has gaseous molecules. Product side doesn't have any gaseous molecules. Reactant side even has 6 gaseous molecules, which is very impressive, considering the other side 0. The effects of a change in temperature. So the value of K changes with the temperature. This is considered the synthesis of ammonia again. So right here we see the same ammonia Haber process. It is an exothermic reaction in this case. So according to Le Chatelier's principle, what you should see is, since this is exothermic, you can write the energy as being a product. Endothermic, you would write the energy as being a reactant because you use the energy up, right? Exothermic, you give off the energy, you produce it. And so, according to Le Chatelier's principle, we would expect, in this case, that a shift will be in the direction that consumes energy. So as you cool it down, you would expect it to go to products. As you increase the temperature, you would expect it to go to reactants. So the concentration of NH3 decreases and that of N2 and H2 increases. Thus, the decreasing value of K. So one of the things I would like to note about exothermic reactions here, by the way, is Le Chatelier's principle does predict, and that is true. So this reaction, as you cool this reaction, it does increase the amount of product you will make. And so yes, it does shift it towards the right. However, there is actually a cutoff, a point of no return. And that is, once you get cool enough, you will no longer overcome your activation energy, which means you won't make any product at all. You won't do anything. It'll just freeze the entire system. You won't have any shifts. You won't be able to establish equilibrium anymore because the reaction just won't be able to go. Okay? So there actually is a funny thing, this Haber process. People have many times, and some successfully by using catalysts, have attempted to make it so you could reduce this temperature. And so a lot of places they reduce the temperature, it makes the more product. Great, you have more ammonia, more fertilizer, you're doing great. Then they get to a point where they get the temperature too low and they get nothing because of activation energy, right? However, if you use a catalyst, you can go even lower temperatures and do this even better, right? So let's consider the decomposition of calcium carbonate. This is an endothermic reaction. So as you increase the temperature, you're going to cause this equilibrium to shift to the right. Because again, your endothermic reaction has energy as a reactant. So increasing the temperature is going to push it towards products, or shift right. Your value of K will increase. If we were to reduce energy, what's going to happen? It would shift R towards the left, away from products. Okay. So right here we actually see a visual representation of equilibrium being affected by temperature. It's kind of a cool thing you can do in labs. So right here we have N2O4 versus NO2. And what we see is when we cool this, we actually get a greater amount of the N2O4, which is clear. And so when we warm this, more of the N2O4 will convert to NO2, and it will shift towards NO2. NO2 is actually the component in smog that makes it very, the brownish color you associate with smog. And so this turns like this reddish brown color. And a very deep red and brown color in this case. There's actually quite a concentration in there. So let's use that. This is a summary of this Le Chatelier principle. Treat energy as a reactant for the endothermic process, as a product for the exothermic process. Predict the direction of the shift in the same way as when an actual reactant or product is added or removed. So let's try this out a bit. For the following reaction, predict how the value of K changes as the temperature is increased. So this negative value of delta H, that means this is exothermic, and that means you're releasing energy, right? And so energy would be a product. So as the temperature is increased, your value of K is going to decrease. Again, energy is a product. When you increase the temperature, you will shift towards reactants. Remember, products are on top, reactants are on bottom for K. And so you're getting rid of this, you're making a smaller number on top and a larger number on bottom. And that would give you a smaller K. And so the equilibrium shifts to the left, of course, and there you go. Anyways, right here is the different shifts for different deals. Hopefully at this point you'll be able to predict these. Honestly, I'm beating a dead horse at this point. Really just practice it, okay? That's the best answer I can give you. Practice. This is not actually a conceptually difficult problem. Le Chatelier's principle is quite conceptually easy, actually. However, there is a little phenomenon that happens a lot with chemistry, and that is the fact that people get nervous because it's chemistry and stop functioning. So, the value of the equilibrium constant, K, this is dependent on what factors? 1. Temperature of the system. 2. Phases of the reactants and products. 3. Concentrations of the reactants. 4. Concentrations of the products. And so there we have our little options. Of course, the correct one is 1 and 2 are the correct ones, which is temperature of the system. Well, we just spent like probably 10-20 minutes talking about temperatures changing systems, right? And so Le Chatelier's principle tells you that the temperature of the system is a major factor on the equilibrium constant. Hopefully you would have even known that, because I really, if you just stepped back and thought, okay, I have different equilibriums, like a salt dissolving in water, etc., right? Sugar dissolving in water, food being different phases, my jello melting and freezing, etc. Ice cream melting and freezing. These are all equilibriums. And the temperature affects how much product versus reactant I have in all of those cases, doesn't it? So it's not. This is something you've seen probably dozens of times a day throughout your life. The next one, phases of the reactants and products. yes, the phases of the reactants and products will affect my equilibrium constant. Depending on whether I have a solid, they will be put into my equilibrium constant, etc., right? All right. So suppose we have the following reaction at equilibrium. What happens to the equilibrium when additional calcium carbonate is added to our system? Okay, so we have calcium carbonate here, we have calcium oxide, and we have CO2. Does anybody notice when you look at these that we have a gas and two solids? So what happens when we add more solid into an equilibrium expression? It has no effect, does it? Because remember, the pure liquids, pure solids, they are not included in my equilibrium expression, are they? And so they don't affect the amounts I have, do not affect my equilibrium. They just don't have any effect on my equilibrium constant. Okay? So suppose we have the following reaction at equilibrium. Which of the following statements is false? A. Adding PCl3 to the container shifts the equilibrium to form more PCl5. So if we add more of this, will it shift the equilibrium to form this? Yes, it will. Yeah, if we add more product, it will shift it towards reactant, won't it? Decreasing the volume of the container shifts the equilibrium to form PCl5. So on this side we have gases, on this side we have a solid. So this has the more gas molecules, doesn't it? So if we decrease the volume of the container, that's going to cause this to shift left towards PCl5. So yeah, that makes sense. Removing PCl5 from the container shifts the equilibrium to form PCl3. Ooh, these are gases. That's a solid again, isn't it? So does it really matter how much of this we have? Not really, does it? And so yes, it is C. It is false. When the following reaction is at equilibrium and the volume of the container is decreased, what are we going to see? And so we have this at equilibrium. On this side we have 1 mole. On this side we have 2 moles of gases. So if we decrease the volume of the container, it's going to go towards the side with less moles of gas. And so that will be the reverse reaction rate increases, i.e. we are shifted towards the reverse reaction left. For a certain reaction at 25 degrees Celsius, the value of K is 1.2 times 10 to the negative third at 50 degrees Celsius. The value of K is 3.4 times 10 to the negative 1. So at 25 degrees Celsius we have that value, at 50 degrees we have this value. And so what we see here is 25 degrees, this value is smaller. At 50 degrees, this value is larger. Larger value indicates we have more product. That would mean as we increase the temperature, we get more product. And so this is an endothermic reaction, meaning we are using energy as a reactant. We increase the temperature, we get more product. Consider the chemical system at equilibrium. The reaction is exothermic, releases energy as heat, as written, and the temperature of the system is raised. Which of the following will be true? Equilibrium shifts to the left. You can read this. I'm dying here. Alright, the correct one is D. The equilibrium shifts to the left and the value of K decreases. And why is that? Well, this is an exothermic reaction, and the temperature of the system is raised. And so this is going to shift away from products, because the exothermic means you can write in heat, energy, as a product. And so it will shift towards reactants. If you lower the amount of products and raise the amount of reactants, the value of K will, of course, become smaller and decrease. There we go, folks. You take care. Have a great night.